This is part 2 of the percent composition and empirical formula kind of application of the math skills for molar mass. And we left off just finishing this talk about number 7 and the scaling factor. We can find it using the molar mass of our molecular formula and our empirical formula to find a certain factor by which they're related. And it's the same by which their formulas are related. And so in this example, we looked at this row here, seeing the scale factor of 6 and how that works out with the molar mass. So we're going to now do an example of actually calculating the empirical formula. And before we start these, there are quite a few steps, but the most important thing that I kind of want to highlight is we don't want to round anything unless we are like at 0.001 or 0.999. We don't want to round up or down. And so in that simplify column, we want our numbers to be almost whole numbers in order to round. And so there's a couple of little notes there, kind of tricks to help us round correctly or kind of play with the numbers a little bit so that we can get to a whole number for that molar ratio in our chemical formula. And because these are real chemical formulas, it will come to be a whole number because the numbers in chemical formulas, those little subscripts, are always whole numbers. So we can count on that working out for us. So we do not want to round, and we'll keep probably a handful, 3 to 5 decimal places until we get to writing that chemical formula. Okay, so that's just a little disclaimer about rounding for writing formulas. So we are going to take our percentages and work backwards to figure out the formula. And when we have percentages, remember it was part over whole by mass. And so if we have 42.9% carbon, we can say, well, if the whole thing is 100, that means 42.9 grams has to be carbon. And so that's what this first column is telling us to do, is say, assume the whole thing is 100 grams because it can really be whatever we want it to be. So that means we have 42.9 grams of carbon. We'll just turn those percentages into mass. And the next thing we have to do now is use molar mass to get them back to the molar ratio. Right now they're in gram ratio, but that's not going to help us to figure out the subscripts because their grams are different on the periodic table. So our next step is to do a little conversion and convert from our grams to our moles using that molar mass on the periodic table. So we have 1 mole of carbon is its molar mass, or its average atomic mass for carbon, 12.01, and oxygen, 16.00. So this will tell me now my molar ratio. And so once I get this calculation, I should be able to then eventually simplify this to a whole number. And so when I calculate this, I'm going to keep a handful of decimal places. So there's my moles of carbon, 3.57202, and my moles of oxygen, 3.56875. Okay. Now, neither of these are very close to being a whole number. So we have a couple of ways that we can simplify this, and the first thing that we usually do to simplify is to simply divide by the smaller of our moles that we just calculated. So I'm going to put a note here because you're going to start with that every time. Well, first we divided by molar mass. Okay, then our first step in simplifying is divide by the smaller amount of moles. And you're going to divide all of your moles by that smaller amount. So this seems kind of generic and arbitrary of like, okay, why am I doing this? This is just kind of playing the game to get whole numbers. So of these 2 moles that we just calculated, They're very similar actually, but our smaller one is our moles of oxygen. So I'm going to divide both of our numbers by this 3.56875. I'm going to divide both of these by that number. And a number divided by itself is 1, so that's going to give us 1 mole of oxygen. And then when we divide our carbon by that number, we get 1.0009. That is safe to round. So we have 1 mole of each of them. And although our percentages are not 50-50, that's what our chemical formula molar ratios are going to end up being. We're going to have CO for our empirical formula because of the mass differences, okay? So we've got our chemical formula, hooray, hurrah. Now we want to see if there is a scale factor to the actual formula, because what we have found here is the reduced version. That's what we did when we simplified. This is our whole number ratio that is reduced. That's why we were dividing. We're just trying to get it as small as possible. And we are going to find its molar mass so that we can compare it to their actual, which is given here, and see if there is some sort of factor that they're related, their scaling factor. So anytime you get that empirical formula, go ahead and find its molar mass. For carbon and oxygen, that's going to be 12.01 plus 16.00. So that's going to be 28.01 grams per mole. There's our empirical formula molar mass. And like we talked about at the very end of the part 1 video and kind of the start of this video, to find that scale factor based on molar mass, you can take the molecular formula molar mass and divide it by the empirical formula molar mass to get your scale factor. And so this one, we can find that pretty easily. 84.03 divided by 28.01, and I get 3. So my scale factor is 3, and that means my formula is going to be scaled up by a factor of 3 for my molecular formula. So here's molecular formula. Here's my empirical formula, the reduced one. And here's my scale factor. So there's all your parts. So I know that was a lot of steps. Let me recap what we did before we do it again. You're going to change your percentage into grams and then divide by molar mass to get the mole ratio. Then you are going to try to simplify it. And the first step we do is divide by the smaller amount of moles. If it's close enough to round, meaning it's almost a whole number, 0.00 something or 0.999 something, then you can round to that whole number. If not, then we'll do a couple of little tricks that are listed here in our simplify box. But we did not need to do that in this case, and you got your reduced empirical formula. Find its molar mass and see if there's a scale factor to the molar mass of the compound to find its molecular formula. Let's try number 5. A sample is made of 40% carbon, that's 40 grams carbon, 6.71% hydrogen, and 53.5% oxygen. So the first thing we want to do is divide these all by their molar masses. Okay, doing a little conversion. Carbon's molar mass on the periodic table, we just used that one, is 12.01. Hydrogen 1.01 and oxygen 16.00. So now we're going to find their moles. So I'm going to get 3.33056. Again, keep a handful of significant figures, which just means decimal places, so that we are not rounding on accident. And then 53.5 divided by 16, there's my oxygen. Okay. Once we have our moles, the best thing we can do is divide by the smallest one to help us start simplifying. The smallest here is our carbon, so I'm going to divide all of them by 3.33056. I'm not going to write that down because I only have so much space, but you're going to divide all by this guy, which will give us 1 mole of carbon. I got 1.99. That is safe to round to 2. And then the last guy here, 1.00, also safe to round. So I've got my subscript numbers. That's what we're simplifying to find. And I can write my chemical formula. C1H2O1. We don't have to write the ones. So there's my reduced formula. I'm going to find now its molar mass, so I can see if there is any relationship to a scale factor of this given molar mass for the molecular formula. So I'm going to add up 1 carbon, 2 hydrogens, and an oxygen to find the molar mass of this compound. And I get 30.03 for its molar mass. And to find a scale factor, I'm going to divide. So I've got 150 divided by 30. This one kind of clearly shows itself. You can still divide them and you'll get 5. And so that means our molecular formula is C5H10O5. Yay! Again, empirical formula, molecular formula, scale factor. You don't have to label those, but I'm just doing it to help you as you go through these examples. If in working through your simplifying section, you get numbers that are not safe to round, meaning they're like 0.5, 0.25, 0.75, even 0.33 or 0.66. I didn't list those, but that one has a little help there too. You can multiply all of the numbers by what's written here to get them to be a whole number. So after you divide them all by the smaller, let's say you get 1, 2.5, and 1. Then what you could do is multiply all of them by 2 to get 2, 5, and 2. So when you're playing with your numbers, you don't want to round ever, ever, ever unless you're 0.00 something or 0.99 something. All these in-between numbers you have to kind of manipulate a little bit to get whole numbers. No rounding, because a chemical formula always has whole numbers, so we can trust that it will work itself out. If we round when they're kind of mediocre numbers like these, then we're not going to get the correct empirical formula. So you will need to use some of these little rules for number 6. I think you only need to use one of them. But if your number has a 0.5 as its decimal, multiply all of the moles by 2. If it has 0.25 or 0.75, multiply them all by 4. If it has a 0.33 or 0.66 at the end, multiply them all by 3. And that will get you close enough to round. So try number 6 on your own, and then we'll go through it together on the Zoom on Thursday to see if you got it correct.